Okay, so here's part 2 of the video, and it's about projectile motion questions, but these are the theory questions. These are the questions that students will often struggle more with than the formulas. Even though the formulas have a whole bunch of mathematics, they're a straightforward process to do. You ask some word questions about it, and it's a bit more challenging, they find, to answer. So this first concept review question, 1.1, you're going to pitch, think about the pitcher pitching 2 baseballs horizontally from the same height at the pitcher's mound. But one of them is, they're going to go at different speeds. One of them is going to be faster than the other one. So they both will, the first one, if one is pitched faster, it would go and pass through, arc downward, but pass through the strike zone. Versus one that is thrown slower, I'll draw that one as an arc in blue, will actually go through and might narrowly miss the strike zone. Both pitched from the exact same height. Why is it, this question's asking, why is it that they fall different distances from the initial height it was thrown? The green one falls this far. The blue one from that initial height has fallen further. The question saying, why does the faster ball not fall as far as the slower one? After all, they travel the same distance. From here to there is the same distance, and they're both being affected by the same gravity. This is the same, that's the same. Why do they fall different speeds? They're trying to set you up in this question. So the part that's different for each of these projectiles is the time it takes to get there. Clearly, the faster ball, the green path, faster ball is falling for a shorter period of time. And so if it's falling for a shorter time period, then that means it falls a shorter distance. It's the time that's not the same for the two things. Sure, they have the same distance. Sure, they have the same acceleration. But they're not falling for the same amount of time. The slower ball takes longer to get there, so is falling for a longer period of time. Therefore, it falls further. Okay? It's the time that's the key, and that's what they don't talk about. Okay? Clearly, if a ball is being thrown faster, it gets there quicker. That means it falls, has the opportunity to fall for less time than if it was thrown slower, takes longer to get there. Therefore, gravity is hauling down on this for a longer period of time, and that's why it drops further down instead of the shorter one. So strike zone versus non-strike, the time is the difference in the question. They're trying to lead you to problems with this information. And smoke and mirrors, they're not talking about time, and you have to talk about it. So for question 1.3, which is the same setup as 1.2, but in 1.2 it asks you to talk about forces. So I want to just park that question of drawing what the forces would look like on it till we get to the dynamics section or forces section. But for right now, if you have a puck that is sliding across the horizontal tabletop at a constant speed, and it flies off the end of the table, it wants you to draw vectors that would show the horizontal and vertical components of the puck's velocity at 4 points. So we want to take this puck that's right here, and we want to draw its speed at 4 different points. right before it hits the ground. Okay, so that should be a parabolic arc that would be flying here as it goes down and smacks into the ground. So we want to draw the horizontal and vertical components of its velocity at 4 points, and then draw the total velocity vector. Okay, so my horizontal velocity, if I take, I'm going to shorten this vector here that I drew before. If I take that and I make it this long, let's say that this blue arrow is Vx. That Vx does not change. So this Vx is actually going to be the same the whole time that the puck is sliding along, or flying through the air. Ignoring air resistance, Vx is always the same. The Vx component is constant. What does change is the Vy component. The Vy component of the puck, over here, there's no y speed downward. There's nothing that goes down on this puck. But at this point right here, the y speed of the puck is a little bit downward. But you were taught that you should draw vectors tip to tail, so you would actually put this Vy over here. Drawing tip to tail the second vector, after a little bit longer, the puck drops a little bit further. It's going faster because it's accelerating. So that would go here. Then it's going faster downwards, a longer vector, tip to tail. And at the end, before it hits the ground, it's going really fast and is much longer, which you draw tip to tail. So your Vy is changing the whole time, getting longer and longer and longer. And the question says, draw what the total velocity vector would look like at each of the 4 points. And I'll draw that in red. So if you have an x component and a y component, if you draw from the beginning of the first to the end of the last, this would be your total velocity. Then more downward, total, more downward, total, and really moving down, total velocity. Okay, and the angle is changing of that red vector, which that angle should be matching the dotted parabolic path. So this question 1.3 was just asking you to draw what the Vx's look like and the Vy's. When I'm marking it, I would be looking that you would have Vx's the same. I would be looking that I see Vy's getting bigger and that you've drawn them in a triangle like you've seen. The Vx, the Vy, and the hypotenuse. Vx, Vy, hypotenuse for all 4 of them. Okay, that would be the expectation for there. There's no numbers. It's just recognizing the physics of the question. Last question. Suppose an object is thrown with the same initial speed and direction on the moon, where g on the moon is actually 1/6 as large as it is on Earth. What will be different? Without going through all of the formulas and working it out, can we figure out just by examining the formulas what will be different? And so will they change and will they become bigger or smaller? Okay, so comparing Earth to moon. So the question tells me it's thrown with the same initial velocity. So I think that the initial Vx and Vy is not going to change. Because that's just how hard you throw it out of your hand. The gravity of the moon does not affect the Vx and the Vy of how hard you push it. So there's no change on Vx or Vy. There's no dependence on gravity for that. Now, how far it goes, how high it goes, how long it's in the air, those are all different factors. But this is just the moment it leaves your hand, is there a dependence on gravity? And no, there isn't. All right, so for part B, will it go in the air longer? I think it makes sense if you're throwing an object on the moon, that if gravity is less, it's being accelerated downward less than it would be on the Earth. So it's probably going to go higher. It's probably therefore going to hang in the air longer, and it's probably going to go further. That's my guess, but let's look at the formulas that we used to figure out how long it's in the air. When we did this formula, what you were looking at, we were taking the y is VIY t 1/2 gt squared. Okay? We were setting y equal to 0. We were taking the VIY over. And we then had 1/2 gravity, t squared. We canceled a time. So you had a formula that said negative VIY over half gravity equals time. This was the formula we've been using over and over again to get to this time. So if I just look at the formula, if I make g smaller, and it's in the bottom of a fraction, if you make that number smaller, then the time will get bigger. So if I look at some numbers, as the number in the bottom gets smaller, from 4 to 3 to 2, these decimals actually, the number actually gets bigger, doesn't it? Okay, as the number, as the denominator gets smaller, the actual value increases. So, as g gets smaller, then t is bigger. And actually, if g gets 6 times smaller, then that means that the t will be 6 times bigger. When you hit a golf ball on the moon, it's in the air 6 times longer than it would be on Earth. Moon golf courses would be freaking huge. What would a par 4 or a par 5 look like on the moon? It would have to be monstrous. Okay, so just examining this formula, the VIY didn't change. The only thing that changed was g. G gets smaller, then the t goes up. If this goes down, this goes up. The denominator goes less, the t goes higher. So the other question then said, how high does it go? How high does it go? How will that formula be affected? Okay, so if I look at this formula, VYF squared equals VIY squared plus 2GY, and solved this one for height, that would be the formula you would use to figure out how high does it go. So you could take VF squared, which you set to 0, subtract VIY squared, divide by 2 times gravity equals y. In this formula, the Vy and the Vf don't change. We said that in the first part A. They stay the same. What do you know? You know gravity is 1/6 smaller. Well, if the thing in the bottom goes down by 6, the thing in the top goes up by 6. Therefore, the maximum height is 6 times bigger when gravity is 6 times smaller. Okay, the less gravity there is, the higher it goes. So the reverse of this would be true. If you were on a planet where gravity was twice as much, the height would be half as big. They do the opposites. If g is 6 times smaller, y will be 6 times higher. The last question, maybe I'm doing them in the wrong order. Last thing it asks is, how far does it go? So, the only formula we used for the last one for range, the range formula was x equals vxt. This did not change. This, however, is 6 times bigger. We said it was in the air 6 times longer. So if it's in the air 6 times longer, then it has to go 6 times further. Okay, so theory question here. If you're playing on the moon where gravity is 1/6 as big, then that means that the object is in the air 6 times longer, it goes 6 times higher, and it travels 6 times further. So basketball nets, you probably want to have 6 times higher as well. Imagine slam dunking on a net that is 6 times higher than what they are on Earth. That would be freaking cool. Like I could slam dunk anything anyway. Anyhow, so that's the theory part of those questions. They're usually quite a bit more challenging. I love these types of questions where as you change one type of variable, what happens to the others. So try to wrap your head around those and we'll talk more about them. You'll see this as a recurring theme through many, many questions throughout the course.